Welcome to EDU World Space.
For this question, we are investigating the decay of a neutron into proton and electron. We want to find the speeds and the momentum as well for these particles. After the decay, we are imagining that this neutron is at rest as it starts, and subsequently, it decays. So we're going to use two different conservation laws. One is the conservation of energy, and then conservation of momentum. Now, to determine the energy that's released in this reaction, we're going to look at what is the change in the masses, right, or the Q value of this reaction. The energy released will be dependent on the change in the mass multiplied by c squared. Right, the change in the mass will be taking the initial mass, which is the mass of neutron, minus away the mass of the proton and mass of the electron. So we can look up table A, point 3 in appendix A. So all of this in terms of atomic mass units. Now putting all of this together, multiplying by c squared, where c squared is taken to be 931.5 MeV per U. Since we are dealing with atomic mass units, so it's very convenient to get our energy in terms of MeV, which in this case would be 0.782. Now for the more tedious parts, we're not going to look at the entire conservation of energy as well as conservation of momentum. So from conservation of energy, we know that the initial energy of the system is simply the rest energy of our neutron. This must be equals to the final energy of the system, where it is now equals to not just the rest energy of our proton and electron, but also the momentum. Right? So we have to account for total energy. And we know that total energy for any particle is given as E squared is equals to P squared C squared plus M squared C4. So basically E is equals to square root of P squared C squared plus M squared C4. And we're going to substitute that in here. So we have the total energy for the proton. Then we have the total energy for our electron. By conservation of momentum, however, we know that the initial momentum of the system is 0. And so the final momentum of our system must also be 0. And so this implies that the momentum of the proton must be equals to momentum of the electron. Right? They must be equal in terms of magnitude, and they are traveling in opposite directions so that they are able to cancel each other out, so that we can get a total momentum to be 0 still. So we can just define the momentum to be just P. We don't have to distinguish between momentum of electron or momentum of proton. Now moving on, we will need to do some simplification to this equation. So the only unknown in this equation is our momentum P. All of the rest of the values can be obtained, right? They are just the rest energies. So in order to simplify this, I'm going to bring the electron, this term over here, to the left hand side, and then I'm going to square both sides of the equation. So this is after squaring both sides of the equation. There's a common term of p square c square, which we can remove. Now we need to get rid of the square roots once again in order to get our p square c square term on the outside, right? So we're gonna put everything that doesn't have p to the right hand side. And from here, it should be quite easy. What you're gonna do is you square both sides to get rid of the square roots. And then I'm gonna subtract this term to the right hand side. So this is just me c square squared. What we're left with now is to just substitute the rest energies into this equation. So the rest energy for electron, 0.511 MeV. Rest energy for neutron, 99.6 MeV. And the rest energy for proton, it's 938.3 MeV. So putting all of this in, and then we can find what is P times C, right? That by taking a square root of the entire expression again, you should get 1.19 MeV. And now we can find the velocity. So what we're going to do over here is going to assume relativistic conditions, right? A more general case, right? Since relativistic condition applies for both low speed and high speed. So the relativistic momentum is gamma mv c. And we're going to try to see whether we can extract out our v. All right. So from here, our gamma is written in terms of v is 1 minus v square c square times m vc. Now we're going to try and simplify this expression. So what we can do is we divide this by mc square, the rest energy. So if you were to take gamma mvc divided by mc square, this will give us v over c from which now we can try to extract our value of v over c. So this is again equals to pc over mc square. We bring the square roots over to the right hand side. So v over c is equals to then we square both sides. Bring all the terms with b square c square to one side, and then we divide the factor away. And then to get v over c, just have to square root everything. And now we just put in the values, right? So PC is 1.19 MeV. MC square, right? Depends on what particle you are looking at. So if you want to look at the electron, in this case you put in 0.511 MeV for electrons. But for protons, you put in 98.3 MeV. And so for protons, you should get a value of, sorry, this should be 3.82 times 10 to the power of 5 meters per second. On the other hand, for our electron, you will get a very close number to C, and in fact in terms of C is 0.919 C, and this tells us that our electron is relativistic because it is actually more than 10% of the speed of light. On the other hand, for the velocity of our proton, it is actually 3 orders of magnitude smaller than our speed of light, and so it is not relativistic.